Welcome everyone. Today we're going to take a look at some applications of geometric vectors, which include force, tension, and velocity questions. So it's important for us to know that in all of these we're creating kind of triangular structures that will help us solve for resultants. And then we can use Pythagorean theorem and variety of trigonometry to find missing pieces of information. If we have two forces acting at the same point, I think I mentioned this in an earlier lesson, the forces can be added or composed in order to obtain the resultant of each of these, and we call this the resultant vector. Okay, so let's take a look at a couple examples. I'll have some information in between some of these as well. So in all of these questions, I should mention that it can be very helpful to create scale diagrams because you can actually check your answers by measuring the resultant if you've created a good diagram, and you can also measure angles with a protractor. So what you'll need for this is a ruler and a protractor. If you can get those and create scale diagrams, that makes your life a lot, maybe not necessarily easier, but you can just be more confident in your answers. Okay, so as an example, for a scale for this one, perhaps you could choose that every 1 centimeter represents 2 kilometers. And then for our 8 kilometer east line, you can draw a 4 centimeter line. And for our 6 kilometer north line, you can draw a 3 centimeter line. Now, we do know that east and north meet each other at a right angle. So we have a right angle here, and then the resultant vector of these two things is going to be the vector that extends across both of these, from the tail of the east vector to the tip of the north vector. We're going to label this resultant. Now, what I'm really interested in here, and I probably should add quadrant bearing in here to specify, what I'm really interested in here is if I have the north line, I'm interested in this northeast direction. So I'm going to call that x, but in order to find x, I also need to find this interior angle theta here. Alternatively, with the z shape, if I find this angle up here, I can simply say that that's equal to x. So we could also label that x. So perhaps maybe we could just do this in a single calculation here by finding that angle x up in the top. Okay, let's start with the magnitude of the resultant. This is a right angle triangle, so I'm simply going to use Pythagorean theorem in order to find this. And you should get a magnitude of 10 kilometers when you enter this in. And in order to just make sure, just in case maybe I got the wrong answer for this, I'll use the two sides that I already was given in the question in order to find the angle. So tan of angle x is going to be equal to opposite over adjacent. You're going to do tan inverse of 8 over 6. Making sure you're in degree mode, make sure you have your calculator out so you can follow along with us. And you should get 53.1 degrees. Now that's this angle inside here. If you found the other one, you're going to simply subtract from 90 degrees and you'll have the correct angle. And that means that this one is also 51.3 degrees using the Z pattern. So when we state our resultant here, we're going to say that the resultant is 10 kilometers north, 53.1 degrees toward the east. Okay, couple setup things that we need to know for velocity questions. So you're going to see things like airplanes and boats in the water with currents, or potentially swimmer in the water with currents. So in all of these, again, we're trying to create scale diagrams as much as possible and create triangles. So in airplane questions, we're looking for things like velocity of the airplane, or airspeed, which means the velocity of the airplane with respect to the air. The velocity of the wind is mentioned. This is, of course, the velocity of the wind with respect to the ground. And the velocity of the airplane after those two forces act on it will be the ground velocity. leading us to the equation that the vector that represents air velocity plus the vector that represents wind velocity should be equal to the ground velocity. Similarly, when we're doing boat questions or swimming questions within water, current is similar to your wind velocity. So this is the speed of the current and velocity of the current with respect to the ground. There's also the velocity of the boat relative to the current. This is like air velocity. And when we sum both of those, we get a resulting ground velocity, and we get a similar equation to what we looked at above. Also, it's helpful to know that if you see the word upstream in a question, it means against the current, and downstream means with the current. Another important thing that you're going to want to watch out for are the words from and to, especially in airplane questions. So I'll give you an example. From the west versus to the west. From the west means a wind coming from the west going toward the east, whereas to the west means something coming from the east going to the west. Let's take a look at an airplane example. We're given information about airspeed and ground speed, and we're looking for velocity of the wind. So just as a reminder, air velocity, or velocity with respect to the wind plus the wind current, is going to equal the resulting velocity with respect to the ground of the airplane. So always helpful again to draw a diagram, and it's ideal if you can create a scale diagram. So perhaps what you can use as your scale for this one is that 1 centimeter is maybe equivalent to every 200 kilometers per hour. If you want your diagram to be a little bit smaller, perhaps you could say 1 centimeter is equivalent to 250 or 500. So let's suppose that this is our air velocity. We've gone north 40 degrees toward the east. And I'm just going to label this as 1,000 kilometers per hour. Now 5 degrees a little bit further, we're going to have the ground velocity, which is 1050. And I know that this is 45 degrees from the north line, making this 5 degrees. Let's zoom in a little bit here. Okay, now we have a resulting vector. If we think about our vector addition, the wind is going to be added to the vector that represents air velocity in order to get ground velocity. So the wind needs to be acting on the air velocity in order to get that ground velocity. So there's our wind velocity. So I have two sides in a contained angle. So in order to find magnitude of the wind vector, I can use cosine law. Okay, so take a second, enter this into your calculator, and you're going to take that value that you get and square root it right in your calculator, leave all the decimals. So you should end up with 10,491 with some decimals on the end. Keep those decimals and square root, which gives us a wind velocity of 102.426. I'm going to leave a few decimals on here until we get to our final answer so that we can make sure that we have an accurate final answer. Okay, so now we have all three sides and we have one angle. I do need to sort of figure out some information inside here. So let's just start by finding, I'm going to call this guy theta. Let's start by finding that angle in there, and then we can discuss a little bit more how exactly we're going to find the direction in either true bearing or quadrant bearing from here. So one really important thing when you're doing these types of questions is that when you have all three sides and you have, let's say, one angle, technically you can use either sine law or cosine law to find the remaining angle here. When we have all three sides though, I would highly suggest that you use cosine law, because when we use sine law, we will have to account for the ambiguous case of sine law. So we discussed that in the first lesson. Whereas if we use cosine law, it's going to tell us definitively what that angle is. Sine law gives us two options. It gives us an acute option and an obtuse option. So in order to avoid that, let's just use cosine law to calculate. So if I'm looking for cos of theta, I'm using its opposite side, which is 1050 to start. I'm squaring that and subtracting the squares of the other two sides. And dividing by -2 times the other two sides. When you get this answer, you're going to do the cos inverse of the value, and that should give you the angle. So take a second and enter this into your calculator. I'm going to do the same. Okay, you should get something like -0.44914, and then you will take the cos inverse of that, keep that in your calculator, and should end up with 116.7 degrees, approximately. Okay, great. So now that we know that angle's measurement, let's just kind of zoom in on what's going on here. It's super helpful just to put a little cross section here, because with the Z pattern right here, I know that this interior angle is also 40 degrees. So if I want to find this angle in here, and the reason why I would want to find that is because I actually really want a southwest direction here. So if I'm looking for a southwest direction, or you can also find, the other option is you could find this and answer in quadrant or in true bearing notation. But I think this one will be a little bit easier to enter in quadrant bearing notation. And it's typical that if we start something in quadrant bearing notation, we'll also answer in quadrant bearing notation. So again, we know that this full angle right here is 116.7. And if I know that red slice is 40, then we can find x by doing the full angle, subtract 40. So that's what I'm going to do here. So x equals 116.7 minus 40, which gives us 76.7 degrees. And this will be a southwest direction. So when you state your resulting wind velocity, you're going to say, let's say round this to 1 decimal place, 102.4 kilometers per hour in a direction south, 76.7 degrees west. Okay, always remember that when we say velocity, we're asking for an answer with a magnitude and also a direction. Let's take a look at a velocity example involving swimming. So for these types of questions, if you're given information about the distances and then also about the velocities, it can be helpful to actually draw two different diagrams. So what I'm going to do with this question, we're given information about how Jordan can swim in still water, that's 2 kilometers per hour. We're told that the river is 200 meters wide, and we're given information about the current and where our swimmer wants to end up. So let's just take a look at our distance information here. If I have a river, I know that that river is 200 meters wide. And it also tells me that Jordan wants to end up at a point 20 meters upstream from her current position. So I do need to consider the current in order to find the upstream location. So if the current is going west, that means that upstream is actually going to be against the current. So she's going to want to end up at a point somewhere up here. I'm going to call that E for end. And that means that this distance is actually going to be the upstream distance. And that current kind of allows me to decide whether the point, oops, sorry about that, whether the point is this way or this way. If it were downstream, then I'd be looking at this distance here. But because it's upstream, we're looking at the green part right here. Okay, so ideally, she wants to kind of head in this direction over here so that she goes straight from her starting location, if she's there, right over to that ending location. So this is actually going to help me find the bearing of the ground velocity. We'll call this the ground velocity. Maybe that's going to be our vector there. Okay, so let's find theta. This is a right angle triangle, so that's going to be nice and easy. We're going to do opposite over adjacent. And in our calculators, we want to do tan inverse of 20 over 200. And if you'd like, you can keep a couple decimals here. I think probably 2 decimals is enough. So 5.71 degrees. And that is going to be this little slice right here. Okay, now that we have this information, we can apply this to a vector diagram. So I'm going to draw a separate vector diagram over here. And Jordan is still going to start here, and she wants to end up at some endpoint over here. So this velocity vector that I drew in the previous diagram is actually still going to be the same. Here's my ground velocity. And you know what? It doesn't necessarily need to extend the entire direction, but we do know that she wants to kind of head in that direction. And we also know that there is a vertical line here, and this is 5.71 degrees. Now we also know that there is a west direction for our current. So I'm going to label that current. And if we use our common sense here, she is going to have to orient herself further to the right of that ground velocity if she actually wants the current to push her over along this path, right? So if I'm thinking about this, if I orient myself in this exact direction, the current is of course going to push me downstream, and that's not what I want to happen. I want to end up along this ground velocity line, so she's going to have to orient herself further over to the right so that then the current pushes her this way, resulting with this ground velocity. So this is going to be the velocity with respect to the current. So just as a reminder, the velocity with respect to the current plus the current should actually give us the velocity of the person or boat, depending on what we're talking about, with respect to the ground. One other little helpful thing is if we draw a little quadrant grid here, we can actually see that there's a little Z pattern, and that Z pattern means that these two interior angles are actually equal. That makes this little slice 5.71 degrees. And I do know as well that the south and east lines make an angle of 90 degrees with one another. So when I add those together to get that full angle, that gives me 95.71 at this location. So I'm just going to erase that and input the angle there as 95.71 degrees. And it can also be helpful if you just kind of name the remaining angles so that you can fill in information where needed. So I'm going to call that theta, and maybe we'll call that x. Actually, I'm going to do that in pink. There we go. Okay, so I know 2 pieces of information here. I know the current is 1 kilometer per hour, and I know that Jordan can swim 2 kilometers per hour in still water, which means that after the current takes an impact on that 2 kilometers per hour, I should expect that the speed I get out from that is a little bit less than 2 kilometers per hour, because she's kind of trying to swim against the current here to compensate for the current pushing her over. So I should expect when I get the velocity of Jordan with respect to the ground that is smaller than 2 kilometers per hour. So let's calculate here. So the first thing that I can calculate, I know a side and its opposite angle, and I know a remaining side. So that actually is going to give me the angle theta in here, which is not necessarily what I need to find the ground velocity, but I do need that in order to find angle x. So let's start there. Sine of theta over 1 is equal to sine of 95.71 degrees over 2. Now, of course, I don't really need to put over 1 here, but usually if this is anything other than 1, we do want to put that side length there. So when I go to isolate for theta, I'm really just doing the sine inverse of sine 95.71 over 2. And if you happened to leave the calculation above in your calculator, you can even use the exact value of the angle if you add it to 90. And that's actually what I'm going to do. I'm going to leave that all in my calculator. I'm going to do sine of my answer, divide it by 2, and take the sine inverse. And I'm ending up here with about 29.84 degrees inside here. So I'm going to label that in my diagram. And because I have 2 angles in this triangle, I can actually find the third angle by simply subtracting these guys from 180. So let's subtract 95.71 degrees and 29.84 degrees to find that remaining angle. So you should get, again, this is a bit of an approximation because we're doing some rounding here, should get about 54.454 degrees. So let's just say about 54.45 degrees. And what this allows me to do now is find the magnitude of my ground velocity using sine law one more time. So let's apply that. And you should use a side and its opposite angle. You can use either. I'm going to use 2 and 95.71. And all you really need to do in order to isolate here is just multiply up that sine of 54. All right, so if you happen to leave the value in your calculator, you can do sine of your answer times 2 divided by the sine of 95.71, and that should give you a very close answer for your ground velocity. I'm going to round this to 1 decimal place since we don't need to use this for more calculations. So this will be velocity with respect to the ground is approximately equal to, I got 1.635. So I'm going to say 1.64 kilometers per hour. So when you state your resultant velocity and the direction, so this is asking us, about the resulting velocity. So the resulting velocity is going to be 1.64 kilometers per hour at a bearing of 0.57. So this is a true bearing. You could also say north 5.7 degrees east. Both of those are acceptable. And this is also asking in what direction should she head. So that's actually her velocity with respect to the current is actually where she wants to orient herself here. So that will be 5.71 plus that 29.84 inside there. And that's actually going to give us the actual bearing that she wants to head herself in. So that's going to be 35.55. And you can say that as a true bearing, or again, you can say north 35.55 degrees east. So she should head let's say 35.6 degrees in order to reach her destination. So this is the velocity with respect to the current that she actually wants to kind of position herself so that the current pushes her over to that resulting ground velocity. All right, so an equilibrant vector is a vector that balances out a vector combination. So it's basically going to balance the resultant vector of a couple of forces. And if we have a resultant vector and an equilibrant vector acting on an object, let's say, and that object is in a state of equilibrium, that's kind of what's holding it there. The opposite of the forces acting on the object is basically our equilibrant vector. So all of these things, if we have the resultant vector and the equilibrant vector, those things are going to balance out to give us the zero vector. And that's essentially what a state of equilibrium means. It means all forces are kind of counteracted and that object is at rest. Okay, so let's take a look at a simple example here. A clown with a mass of 80 kilograms is shot out of a cannon with a horizontal force of 2,000 newtons. The vertical force is the acceleration due to gravity, which is 9.8 meters per second times the mass of the clown. We want the direction, magnitude and direction of the resultant force, and the magnitude and direction of the equilibrant force on the clown. So let's say this is our cannon. The clown is shot out at 200 newtons. Now we also have a force that's acting on this clown, which is pulling it down, and this is the force of gravity. So if we're given the weight, we can find the force that's acting on that by multiplying the mass, I should say, by multiplying the mass of that object by the acceleration due to gravity, and that should give us 784 newtons. Okay, the vector that results from that is going to be this vector here, and we'll call that the resultant vector. Okay, and I'm going to find this angle in here, and we'll just say with respect to the horizontal when we find the angle. So in order to find the magnitude of the resultant vector, I'm just going to use Pythagorean theorem here, since this is a horizontal and a vertical force. And when you get that answer, you're just going to square root that in your calculator. So just enter it in quickly here. And we're left with 2,148.175 newtons. Okay, we can round this guy, let's say, to 0.2 newtons. Okay, now I'm going to find the angle in here. As I mentioned before, maybe we'll just use tan so that we can use the sides that we've already been given. And that would be opposite over hypotenuse, opposite over adjacent. Do tan inverse of that value, and we'll have our angle. So that gives us 21.4 degrees. So when I state the answer for the resultant vector, this is for part A, I'm going to state the answer all together here with the force and the direction. So we're going to say at an angle of 21.4 below the horizontal. All right, now for part B, it's asking us for the equilibrant force, and the equilibrant force is the vector that is opposite to the resultant vector, but equal in magnitude. That was not great. Sorry. Here we go. So there's our equilibrant vector. I also know if I kind of extend this horizontal line a little bit here, that these angles are opposite to one another. So if I know that this angle is also equal to 21.4, I can find this rotation from the horizontal in a clockwise direction. So the equilibrant vector needs to be equal in magnitude, so it's going to be exactly equal to that resultant force, but opposite in direction. So in order to find, let's call this x, I'm going to subtract 21.4 from 180. giving us 158.6 degrees. So we're going to state the direction as 158.6 degrees to the horizontal, or maybe we'll say above the horizontal. Now I'm not really going to indicate a direction here because technically you could have drawn this diagram in the opposite direction that I drew it in. Okay, we don't really have much information as to whether the clown was shot this way or whether he was actually shot this way. So there's a couple ways that you could have drawn your diagram here. So I think if we say 158.6 above the horizontal and we have that supporting diagram there, that should be good. But if you want to answer it based on your diagram, in this case, it would be in a counterclockwise direction. Okay, and then we're just going to finish off here with a couple tension questions. So we have a mass of 20 kilograms. It's suspended from a ceiling by 2 lengths of rope that make an angle of 60 degrees and 45 degrees with the ceiling. Determine the tension in each of the ropes. So we're going to start by drawing a diagram here. And you're going to notice here that I've drawn the rope that makes an angle of 60 degrees with the ceiling a little bit shorter than the one with the 45 degree. And that should kind of make sense because if I have a rope making 60, of course that angle needs to be larger there, and the mass is going to kind of hang closer to that shorter rope. So this should kind of make sense. We should also kind of understand here that if I have a mass that's closer to a certain pivot point on where the rope meets the ceiling, that there's going to be more tension in that particular rope than the opposite rope. So I should expect the tension in this first rope here that's making the angle of 60 degrees to be greater than the tension that's making that the rope is making with that 45 degree angle. So here's a couple forces that we have. Let's call this tension 1. That's going to be the greater tension. Also have tension 2. Maybe I'll draw that as a smaller vector. And these two things together need to counteract the force of gravity on our mass. So I can find the force of gravity again by doing 20 times 9.8. And that's going to give me a force of 196 newtons. Okay, so let's just kind of put these together here. I've got a first tension right here. Maybe I'll blow this up a little bit. And that tension is going to be larger than this other tension here. And I have a force of gravity, which is going to act on this. And my equilibrant vector is actually going to be the vector that is the sum of both the tensions that counteracts the force of gravity. So if this is my force of gravity, I have an equilibrant vector up here, which is equal in magnitude but opposite in direction. That should add up to both of my tensions. So the tension is keeping that mass in a state of equilibrium. Okay, so there's kind of what's going on with our vector diagram. Force of gravity and the equilibrant vector are canceling one another out, and tension 1 and tension 2 need to add to the equilibrant vector. What I also like to do in order to complete my vector diagram is if you draw a couple horizontals in here, it's super helpful to kind of get a visual of what's happening with the angles in here. So here's what I know. Let's look at this angle right here. This angle is the angle between the horizontal and the first tension vector, which is essentially this angle inside here. So I know that that is 60 degrees. Okay, now let's look over here. This angle right here is basically the angle that the second tension vector and the horizontal make. So I know that this angle up here is 45 degrees. Okay, additionally, let's just erase this for a second here. Additionally, I know that this is a Z pattern. So that tells me that this must be 60 degrees in here. And I can also see another Z pattern in here, which also makes this interior angle 45 degrees. Okay, another thing that I know is that the force of gravity and a horizontal need to add up to 90 degrees, making this interior angle 30 and this interior angle 45. Okay, now let's erase all the stuff that we don't really need here, now that we have all those interior angles. Great. And I'm going to also add these two together to get a whole angle of 105. Okay, if you'd like to draw maybe a separate diagram that has kind of the simplified version that we just created here, go ahead and do that. You've got lots of space. Okay, so I have all three angles inside and I have one side. So we should be able to just use sine law with their opposite vectors here. Or not opposite vectors, but opposite angle and side measurements in order to find tension 1 and tension 2. So let's start with the first tension. The magnitude of this tension over the sine of its opposite angle should be equal to the equilibrant vector's magnitude over the sine of its opposite angle. And then we're just multiplying up the sine of 45. Okay, so entering this into our calculator, you should get about 143.48. So let's round this guy to 143.5 newtons. Okay, and then we're going to do a similar thing with tension 2. Now looking at the angle across from tension 2, which is 30. And I'm just going to use the same ratio for the other side there, and we're going to multiply up the sine of 30. Okay, so let's enter that into our calculators as well. And go ahead and round this to the nearest tenth. Should get 101.5 newtons. Okay, as I said, this should make sense because the tension in the shorter rope is actually going to be greater than the tension in the longer rope because the mass is closer to that point on the ceiling. So tensions and shorter ropes, if you have multiple ropes on an object like 2 ropes, this should be expected. We don't really need to do direction for these guys because we already have their angles that they make with the ceiling. So it's not really necessary that we find an angle of those tensions. Okay, last example for today. A video projector of mass 2 kilograms is hung by a 5-meter rope from the ceiling. The projector is pulled back 2 meters, measure it horizontally by a horizontal force. Find the magnitude of the horizontal force and the tension in the rope. Okay, here's our ceiling. Here's our mass. This is 5 meters. Now imagine that you take this and you pull it back horizontally. Now what's going to happen, because this is on a rope and that rope is not going to change its length, is that when you pull it back, it's going to kind of go up in this direction. So it's going to kind of curve. And when we pull it back, let's say to here, it's now here. And this is still 5 meters. This is a 5-meter long rope. Now the length of this is kind of irrelevant, but we still do need this vertical line here because I know that this length from here was pulled back 2 meters. And I know that that's a right angle. This is going to help us because it's going to give us information in order to help us find the angle later. So what are the forces that are acting on this object? Well, the first force that's acting on this object is the force of gravity. And of course, we know that the force of gravity can be found by doing 2 kilograms times the force of gravity, which is going to give us 19.6 newtons. Other forces acting on this object. Well, there's another force, a horizontal force, which is pulling the projector this way. And if we take a look at the sum of the horizontal force and the tension in the rope, that should actually counteract the force of gravity. So if we were to kind of add these up, here's our vector diagram. We have a tension. We have horizontal force. And we have this force of gravity, which we said was down here. And we have its equilibrant vector, which is counteracting the force of gravity. So the two things that are creating our equilibrant vector are the tension and the horizontal force, which cause this to be in a state of equilibrium. So when we kind of look at that in our diagram over here, this vertical force and this horizontal force here, if I find this angle, I should be able to find the resulting angle inside here, and that will give me this. Okay, I also know that the equilibrant force should be equal to 19.6 newtons. And if I can find the angle in there, I know that these need to add to a right angle, so I should be able to find the remaining information. So let's start with this. Let's find this theta. I'm going to use the 5 meters and the 2 meters to help me out with that. So think about just this triangle over here. Just focus in on that for a second. If you look at that triangle, I'm just going to draw it out off to the side here. We said we had a 5 meter rope. This was a right angle, and this was 2 meters. So this is what I want to start by finding. Let's find theta, and then I'm going to find this angle, knowing that these meet at a right angle. So we have adjacent and we have hypotenuse. Let's use cosine for this. And we're going to do cos inverse in our calculators. And let's round to 1 decimal place here, 66.4 degrees. Okay, maybe we'll come up with a bit of a better name. Maybe this can be x. So now let's find x. X is going to be equal to 90 minus that value, which gives us 23.57, so it's going to round to about 23.6. Okay, if you want to be a little bit more accurate with your answer, you can maybe leave 2 or 3 decimal places. But I think that gives us a good idea. I'm going to put that into our diagram now. And because this is a right angled triangle, I should be able to now find the magnitude of the tension and the magnitude of the horizontal force. So just using SOHCAHTOA, no need for sine law and cosine law in this guy. Okay, this will be our reference angle. That makes this hypotenuse, this is adjacent, and this is opposite. So let's start by finding the horizontal force. The magnitude of the horizontal force can be found if we use opposite and adjacent, which is tangent. Okay, so we're simply going to multiply 19.6 up, and we'll multiply it by 10. I actually left all the decimals in my calculator from this, so my answer might be like a little bit more exact here than what you get out if you already erased that from your calculator, but I got about 8.55 newtons. And then we'll find the hypotenuse or the tension. And you can really use any trig ratio for this. I'm going to use adjacent and hypotenuse because adjacent was kind of something that was given to me in a sense, although you did have to calculate it, so hopefully you did that right. So it'll be adjacent over hypotenuse, which is the magnitude of the tension. Multiply the tension up, divide cosine out, and we will find this by doing 19.6 divided by the cos of 23.6. Okay, so we should get a tension that is approximately equal to 21.39 newtons. Okay, and I guess we can use the approximation symbol over here for this one as well.